Okay, we'll go ahead and get started. Can everyone see my slides and hear me?
Yes.
Thank you. Okay, so what I'd like to do today is I'd like to go and just briefly review the answers for quiz number 4. And then we'll go on from there and finish up chapter 8. In terms of what we have coming up, next Monday, the 23rd, we'll have exam number 4. And exam number 4 will cover chapters 7 and 8. So this week, review quiz 4 today, finish chapter 8 today. Wednesday, we'll cover chapter 9. And then next week on Monday, we'll have the exam on chapters 7 and 8. The other thing I wanted to mention is that we still have one more quiz to take, quiz 5. That's going to be a take-home quiz. I'll hand that out sometime next week, and that will cover chapter 9. Any questions about any of that stuff? Okay. All right, so quiz number 4 covered chapter 7. The first question, calculate the effective nuclear charge for the outermost electron of silicon. So what you needed to do on that was look up the atomic number of silicon, which is 14, and then subtract out the number of core shell electrons. So in other words, that noble gas electron configuration. In this case, that's a value of 10. So 14 minus 10 was 4. The second question, calculate the effective nuclear charge once again. And this time is for the outermost electron of magnesium, but now you're going to use Slater's rules. And so with that, you needed to write out the electron configuration. So for magnesium, it's 1s2, 2s2, 2p6, 3s2. And its atomic number is 12. So it's 12 minus, so in other words, to get that shielding value, you needed to use the Slater's rules. And so those rules tell us that it's 0.35 times the number of electrons that are in that outer shell N number. And so we don't count the electron that we are calculating for. So in this case, we have 3 2s electrons. So we're looking at one of those. So it means we only have one that we use in our calculation. So we have 0.35 times 1, and then minus, for that next level down, it's 0.85. We have 8 of those. So we have 2 2s electrons and 6 2p electrons, total of 8. And then for that levels below that, N minus 2 and more, we have, in this case, we have a 1s2 orbital. So we have 2 electrons in that. So if we go ahead and do that math, we get a value of 2.85. So those were the only 2 questions that were any calculations necessary. The rest of them were questions and balancing equations and things like that. So the bonding atomic radius, or the covalent radius, that's defined as half the distance between the nuclei in a bond. Number 4, an increase in effective nuclear charge draws valence electrons closer to the nucleus. That's true. Number 5 is in an isoelectronic series, ions have the same number, and the answer for that is electrons. Number 6, either increasing the effective nuclear charge or increasing the distance from the nucleus results in a higher ionization energy. That's false. If you decrease the distance from the nucleus, then you have a higher ionization energy. So effective nuclear charge, that was fine, but it was the increasing, that was the false part in terms of that distance. Number 7, which of the following is not a characteristic of metals? And the answer there is acidic oxides. So they don't form acidic oxides. Number 8, 9, and 10 were all balancing equations. So the first one, SO3 plus H2O going to sulfuric acid. The second one, potassium oxide plus water going to potassium hydroxide. And the final, calcium plus iodine going to calcium iodide. The one comment I will make on the balancing the equations thing is you needed to write the equation so that it was the two reactants and then going to the product. If you had it backwards, you lost some points on that. So it needed to be balanced, it needed to go the right direction, and the coefficients needed to be correct as well. And then finally, you had to form the correct product to get the full points. So any questions about the quiz?
I have a question about number 1.
Uh-huh.
Can you explain how you determined 10 to be the inner electrons?
Yeah, so if you look on the periodic table and you find, in this case, it was silicon, which is 14. What you look for is the number of electrons for the noble gas configuration that is part of that electron configuration. So if I look on the periodic table, I see that neon is the last noble gas before silicon. And so the neon has 10 electrons in it. So it's kind of like, if you recall, when we talked about writing some electron configurations, you can write them out so that you list everything starting at 1s and go all the way through to whatever element it is. Or we could do a shorthand version where we would put the noble gas in parentheses and then just write out the valence electrons after that. So basically it's all the core electrons, and we define the core electrons as that noble metal kind of set of electrons. Does that make any sense?
So it'd be like the configuration of the noble gas above it.
Yes. Yeah.
Okay. Thank you.
So like in that case, it was silicon, but if it was aluminum or phosphorus or magnesium or any of those, it would still be 10. We wouldn't go, it would be 18 for argon if we then were potassium or calcium or germanium or any of those in that next row.
Okay, thank you.
Okay. Any other questions about the quiz? Okay, let me pull up the slides then. Okay, so hopefully everyone's seeing the covalent bonding slide. So this is where we left off last class, where we started talking about bonding, in this case, covalent bonding. And as we've said is most of the bonds are covalent bonds. And what we're going to do today is we're going to talk about covalent bonds, and we're also going to start talking about how these electrons are shared between the different atoms when we have covalent bonds. So we said before that there's different properties that influence how these electrons in the bond interact. Remember, if we look over at the bottom right-hand corner, the kind of the blue electron density map there, we said that when we're talking about covalent bonding, what we're talking about is the electrons that make up that bond. And you have this higher electron density between the nuclei of the two atoms. So we have a lot of things going on. We have attraction between the electrons and the nuclei. We have repulsions between electrons. We have repulsions between nuclei. And a result of all this kind of stuff going on is that a lot of times you don't get equal sharing of those electrons. So some of the things we talk about today and the rest of the chapter concern how we describe that sharing of electrons and how the two atoms share those electrons really influences a lot of the properties of the compounds that they make up. We talked a bit about the Lewis dot structures. And so once again, we think about that noble gas configuration. And so we're trying to achieve that as we share these electrons. And so that kind of feeds back into our octet rule and trying usually to get 8 electrons or 8 dots around the atom. We go back to a periodic table, and we were talking about how if we looked at the periodic table, and especially for the 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A elements, that number in the group, so that number in the column, tells us how many valence electrons that atom has. And so what we're trying to do is figure out the simplest molecule arrangement for the nonmetals that we can get to kind of complete that octet. So in other words, to get the 8 dots around it. And we have some examples here. We see HF, where fluorine we know has 7 electrons around it because it's in the 7A group. And we see that if we share 1 electron with hydrogen, and hydrogen only has the 1 electron, then we're able to complete the octet in that fluorine atom. We see a similar thing with H2O, water. We know oxygen has 6 electrons around it because it's in the 6A group. By sharing 1 electron with each of those hydrogen atoms, we complete the octet around oxygen. Nitrogen, that's the 5A group. So we have 2 lone electrons, a lone pair of electrons on the nitrogen, and then we have the 3 electrons that are being shared with the hydrogens, and that allows us to get an octet around nitrogen. And then finally, carbon, that's a 4A element. So we have 4 electrons there. And so by sharing an electron with each of those 4 hydrogens, we fill out the octet of the carbon. So that's kind of the goal of what we're doing when we're talking about these non-metal type of compounds forming. And remember, we said that covalent bonds, usually those involve nonmetals. When it's a metal and non-metal, then that's the ionic bonds that we talked about last class. So some things to remember with electrons when we're talking about Lewis structures. When we talk about lone pairs of electrons, and when I say lone pairs of electrons, if we go back to this previous slide, those are the dots, like the 6 dots on fluorine, the 4 on oxygen, the 2 on nitrogen. So in that fluorine, we would say there are 3 lone pairs. A lone pair just means it's not involved in a bond. On that oxygen and water, we would say there are two lone pairs. And then finally, on that nitrogen and NH3 and ammonia, we would say there's one lone pair. The carbon, because all the electrons are involved in a bond, there are no lone pairs. So just remember, when we're talking about these Lewis structures, that's what we're talking about when we say lone pairs. So the lone pair, as it says here, are only on one atom in the Lewis structure, so they're not shared. The shared electrons in a Lewis structure, you can either draw them as the two dots or a one or a line, but not both. And you see, once again, going back to this slide, in this case, rather than drawing the two dots between the hydrogen and the fluorine or the hydrogen and the oxygen, we have the line, which implies that there are two electrons there. We saw this in the lab, the one computer lab, the idea of multiple bonds. So if the atoms are sharing one pair of electrons, we say that's a single bond. If there's two pairs of electrons that are shared, then that's a double bond. And then finally, if there are three pairs of electrons that are shared, we say that that's a triple bond. And we have a couple of examples here, one of a double bond and one of a triple bond. And one way that you can figure out if you need to do a double or triple bond is to satisfy that octet rule. So if we look at the CO2, where we have two double bonds to the oxygen, if we didn't have that, then it would be difficult to satisfy the octet rule around that carbon. The nitrogen, we have a triple bond. Once again, we're trying to satisfy that octet rule. I mentioned earlier that in covalent bonds, those electrons, even though we draw them as being shared, the sharing is not always equal between the two atoms. And when we try and describe what's going on when we have sharing of electrons, but it's not an equal sharing, we use it, one of the terms we use is polarity. And we talk about polarity of the bonds. You'll learn a little bit later that we also talk about polarity of compounds. But bond polarity is a measure of how equally or unequally the electrons in that covalent bond are shared. If it's a nonpolar covalent bond, then we say it's shared equally. If it's polar, then one of the atoms has a greater attraction of the electrons than the other. So in other words, the electrons kind of favor one atom versus another. So nonpolar, the electrons are shared equally. Polar, the electrons in that bond move more towards one of the atoms than the other. So at the bottom here, we have several compounds, all of which involve fluorine. And if you look at the color scale that they give us, is the blue is the lower electron density, red is high electron density. And so just by looking at this color coding, we see that for F2, it's pretty much the same color across. So what that tells us is that those two fluorine atoms are equally sharing the electrons. So in that case, since the electrons don't favor one of the atoms, we would say that's nonpolar. So in other words, equal sharing of electrons equals nonpolar. When we look at HF and lithium fluoride, what we see is we see for HF, we see a tilting, so more red over to the fluorine side. And then for lithium fluoride, we see even a greater portion of red over by the fluorine. So remember, for HF, the hydrogen is going to be positively charged, the fluorine is going to be negatively charged. Lithium fluoride, same thing, lithium positive, fluorine negative. And what we see is that more electron over towards the fluorine in each of these cases, and even more so for the lithium fluoride molecule than the HF molecule. So because this electron sharing is not equal, it's tilted in each case over towards the fluorine side, we say that these are polar bonds. And since these are polar bonds, and this is the only bond in the compound, we would say both of these are polar compounds. We also, if we were going to rank these just by going by the color coding we're given, we would say lithium fluoride is more polar than hydrogen fluoride because there's more attraction of the electrons to the fluorine in the LiF than the HF. So there is a property of the elements known as electronegativity. And electronegativity is the ability of an atom to, when it's in a molecule, to attract electrons to itself. And so in the periodic table, there are some trends that we see. One is as you go from left to right, electronegativity increases. And then when you go from bottom to top, it increases. So a table that you want to keep in the back of your mind and you want to be familiar with is this table, this color-coded table that we see on this slide. This is a really important table to look at. In this presentation of the periodic table, what we see is the elements that are in the upper right-hand corner are the most electronegative. The ones that are in the bottom left-hand corner are the least electronegative. So what this tells us is, especially in this upper right-hand corner, is remembering that fluorine is the most electronegative, and oxygen, nitrogen, chlorine, those those four are the most electronegative elements. So if they're involved in a bond and you see them in molecules, then you know they're going to be polar. The bond's going to be polar, the compound's going to be polar. And as you'll see in a little bit, understanding whether something is polar or nonpolar gives us some clue about the behavior of the molecule. So if you don't remember anything else from this slide, remember upper right-hand corner, most electronegative. And so fluorine attached to anything other than another fluorine, it's going to be the most electronegative atom in that bond. So, as I said, we were talking about polarity of bonds and sharing those electrons. When we say that sharing is unequal, we say it's a polar covalent bond. Because of this, we'll also have polar or nonpolar compounds. So there's two ways that we typically write this sharing of electrons. And that's the two examples that you see at the bottom. So there's that little delta sign where there's a delta plus and then a delta minus. The delta plus on the hydrogen, the minus, delta minus on the fluorine. That indicates that the charge favors going to fluorine. Because remember, we're talking about electrons. So if one of them has more electrons present than the other, it's going to be negative because electrons are negatively charged. The other way that this is often represented, and I think this second way is probably the more common way, will be this arrow with a direction on it, and the direction points to where the electrons are flowing. And so you have a little plus there over the hydrogen, then the arrow going over to the fluorine, and that indicates that that in the bonding, the electrons are favoring being pushed over more towards the fluorine. And that makes sense to us in this case, because we go back to our periodic table chart that we had here for electronegativity and see that fluorine is the most electronegative. So hydrogen has a value of 2.1, fluorine 4.0. So that tells us that fluorine is quite a bit more electronegative than hydrogen, which leads to this type of representation that we see on the bottom here, showing that in terms of polarity, yes, this is a polar bond, and the polarity favors the fluorine. So the greater the difference in electronegativity, so going back to that table and seeing those values, the bigger the difference in those values in electronegativity, the more polar is the bond. So here once again, we have some examples with hydrogen looking at those halogens, fluorine, chlorine, bromine, iodide. And what we see is, just as we would expect, as we go down that column, that halogen column, that we get less of electronegativity difference. And so then it's less polar, and that dipole moment changes as well. Remember, dipole moment is related to polarity as well. So we see going down the table, we see bond lengths going from 0.92 to 1.61. So we see an increase in bond length as we have less polarity. We have our electronegativity difference going from 1.9 all the way down to 0.4. So we see that decreasing as we go down that column. And then finally, dipole moment, which is going to be related to that electronegativity difference, that goes down as well. And you see those values are pretty similar. So once again, I'll say it again, going back to this table, this representation of the periodic table here with electronegativity values, we see that electronegativity increases as you go from left to right, and it decreases as you go from top to bottom, or think of it as increasing going up. So it results in that upper right-hand corner, those are the most electronegative elements. So when we have two elements together, we can look at this table and see what their electronegativity values are, and we can get a feel for how those electrons are shared in that covalent bond. And just remember, when we talk covalent bonds, we're almost always talking about the nonmetals, okay? There's some exceptions to that, but you look up here and really we're talking about these red ones and then the yellow ones over on the right-hand side. Those are our nonmetals for the most part. And so that's the ones that we're really talking about when we talk about these polar bonds. So another term I want to introduce, which centers around, once again, this whole concept of polarity and sharing electrons in that, is a dipole. So when you have two equal but opposite charges, in other words, a cation and an anion, or plus or minus, and they're separated by a distance, a dipole forms. And the dipole moment you can calculate. And that's based on the distance and the charge. When we have a molecule in which the positive and negative charge don't coincide, you have a polar molecule. So this is just an extension of what we were talking about with polar bonds. When you have polar molecules, what you're doing is you're looking at those different bonds that are going on or taking place within the molecule. And then you're kind of looking at the overall polarity of it. In other words, do you have a lot of polar bonds within the molecule. If you do, then the molecule itself is going to wind up being polar. If you don't, then you will have a molecule that's nonpolar. So an example of one that is nonpolar are the alkanes. So remember, we talked about alkanes were carbon and hydrogen. That's all that was in an alkane. So if you look at that, neither of those, either hydrogen or carbon, are very polar. So in that case, you don't have a big polarity difference. And so alkanes, for instance, are nonpolar compounds. You have things that have nitrogen in it, oxygen. If you go back once again to our table, we see that nitrogen and oxygen are two, along with those halogens, fluorine and chlorine. Those are ones that are in red. So those are high electronegative elements. So if you start seeing oxygen and nitrogen in a molecule, then that's a tip-off that you're going to have polarity going on. Remember, I mentioned the alkanes. If we look at those values, hydrogen's 2.1, carbon's 2.5. So those are about the same. You don't have a big difference there to shift the sharing of the electrons from one to the other. But you start getting up to some of these other molecules, some of these other atoms, and nitrogen, oxygen, fluorine, those ones, chlorine, of course, those are ones that you start seeing more polarity differences. So a big thing about polarity is that it determines a lot of chemical properties. And so polar molecules, say in a solution, for instance, will align with positive end of one molecule to a negative end to another. The negative end can align with a positive ion if there's ions present, and a positive end can align to a negative ion if there's negative ions present. Another trait, which is on a more physical level, is you may have heard the term like dissolves like, and that's speaking about polarity. So polar molecules will dissolve polar things, other polar molecules. Non-polar molecules will dissolve non-polar molecules. So it's a polar molecule will not physically dissolve a non-polar and vice versa. So that's why if you ever have, say, like grease in a pan and it solidifies, and you try and wash it off with just water, it won't work, because that grease that's solidified is very nonpolar. Water is a very polar molecule, and so that polarity difference doesn't work. You add some surfactant, some soap to it, and then you can usually dissolve the grease, because that will have a nonpolar functionality on that molecule, and that allows it to solubilize that nonpolar grease. So like dissolves like is the other thing, and that, to be honest, that's one of the big things that you get out of understanding polarity of things. When you're trying to dissolve things, and you think of, why do I ever want to dissolve things? Well, pretty much all cleaning things, whether it's cleaning clothes or cleaning the kitchen or cleaning the bathroom or any of that, it's dissolving things. Like dissolves like. Okay, we talked before that when we're trying to decide if a compound is ionic or covalent, the easiest way to remember that is metal plus nonmetal is ionic, nonmetal plus nonmetal is covalent. But at this point in this semester, you probably know there's always exceptions to these rules. So this is a pretty good rule: metal, nonmetal, ionic, nonmetal, nonmetal, covalent. But there are exceptions. One is that for the metals, if you get to some of the higher oxidation numbers for the metals, then you can get covalent bonding. That electronegativity difference, you can use that to figure some of this out, but that table doesn't really talk about oxidation numbers. In terms of properties, if it has a lower melting point, that usually means that you have covalent bonding. let's talk about writing Lewis structures again, focusing on the covalent molecules. So when we draw these Lewis structures out, these dot structures, there's kind of a process we can go through to help us keep track of things. The first thing is you want to sum up the valence electrons from all the atoms. And then also take into account that overall charge. And so if the overall charge of the compound is negative, so if it's an anion, you have to add an electron to the total for each one of those negative charges. If it's a cation, then it means it's lost an electron for each positive charge. So you would subtract one electron for each of the positive charge that's present on the molecule. So let's take this PCl3 as an example. So for phosphorus, we'd look at the periodic table and we would see that phosphorus is in that 5A group. So that means we have 5 electrons around it, 5 valence electrons. And then for chlorine, we would look at the periodic table again and see that that's in the 7A group. And so there's 7 electrons around that. So we have 3 of those chlorines, 1 of the phosphorus atoms. So it would be 5 plus 3 times 7 for a total of 26. So now we know we have 26 electrons to work with, because in this case, the molecule is neutral, so we're not adding or subtracting any because of a charge. So let's see how we can distribute those 26 electrons and see if we can satisfy our octet rule. So the first thing we do is we write that central atom, the phosphorus. And then we show if we connect each of those chlorines to it, we see how many electrons that takes up. So in this case, we're just going to use the line to represent 2 electrons that are shared. So we have 3 chlorines on there. So each of those involve 2 electrons being shared. So we have a total of 6 electrons that we've used just by connecting the chlorine atoms to the phosphorus atom. So now we're down to 20 electrons we still have to place around. So the next thing we want to do is complete the octets for the atoms that are bonded to our central atom. So now what we've done is we've gone ahead and we've added 6 electrons to each of the chlorines. So that's the 6 dots that you see around each of the chlorine atoms. That gives us complete octets for each of those chlorines, the 6 lone electrons for each, so 3 lone pairs around each chlorine, plus the shared pair with the phosphorus. So that's a total of 18 electrons that we've added. So now we started with 26, we used 6 in the bonding electrons. Now we've used 18 more up with the lone pairs around the chlorine atoms. And so if we subtract that 18 from the 20, we're left with 2 electrons. So we have 2 more electrons that we can distribute. We can go ahead and put those on that central atom, in this case, the phosphorus. And so we now have 2 electrons there around the lone pair around the phosphorus. We see that we've satisfied the octet rule for the phosphorus. So we've got 6 electrons involved with bonding and then 1 lone pair, so 2 more. So now we've satisfied the octet for all the atoms. We've used up all the electrons that we had to work with. Since everything balanced out, that tells us that these are all single bonds. We don't need to do any multiple bonds, double or triple or anything like that. So that's kind of the process you go through to go ahead and write the Lewis structure for the compound. So there are instances where you don't have enough electrons to have that central atom have an octet. And that's where you have to go and kind of play around with a little bit and see if by having either a double or triple bond gives you enough to form an octet around that central atom. So here's an example of hydrogen cyanide, HCN. And so with hydrogen, we just have that one electron, and we know we don't complete the octet on that because of where it's at in the periodic table. So there's not much we can do on that side. We're going to have that sharing of electrons between the hydrogen atom and the carbon atom. But now if we draw it with a single bond from carbon to nitrogen, we see that we can complete the octet on the nitrogen, but the carbon only has 4 electrons around it. It has 2 shared with the hydrogen and 2 shared with the nitrogen. So in order to get that octet satisfied for the carbon and the nitrogen, if we take 2 electrons, two of the free pairs of electrons around the nitrogen, and then convert that into bonding electrons and make that triple bond between carbon and nitrogen, what we see is now we have 8 electrons, in this case, 8 bonding electrons around the carbon. We have 6 bonding electrons around the nitrogen, and then 2 lone pair electrons around the nitrogen also. So we've satisfied the octet rule for carbon and nitrogen both. So this is an example of, by making a triple bond, we satisfy our rules to form the octet. So there's something called formal charge. And formal charge is the charge an atom would have if all the electrons in the covalent bond were shared equally. So the formal charge is defined as the number of valence electrons minus half the bonding electrons, and it's half the bonding because we're sharing it, so we're assuming it's shared equally, minus all the non-bonding electrons. So the non-bonding electrons are those free electrons, so the ones that the dots that you see rather than the lines that indicate a bond. And this can help us determine the structure. And so here we have an example down below for CO2 to try and understand which of these choices is the one that we think is the correct. Because you can see for CO2, we have 2 choices. One is we can have carbon with a double bond to oxygen and a double bond to the other oxygen. And if we look at our Lewis structure, that all balances. Or we could have a CO2 drawn where we have a single bond to one oxygen and a triple bond to the other oxygen. So if we go through this process, excuse me, if we go through this process, we see that valence electrons for oxygen are 6, valence electrons for carbon are 4. We know that because of where they are in the periodic table. We know that oxygen is in the 6A group, so that tells us we have 6 valence electrons. Carbon's in the 4A group, that tells us we have 4 valence electrons there. So that's how we knew the valence electron numbers, was based on where it is in the periodic table. And then we have the electrons that are assigned to the atom. So in other words, for electrons assigned, it's 6 in this one with the 2 double bonds. It's 6. It's the 2, 4 free electrons, and then 2 shared electrons, because those are double bonds, so 1 of each. Carbon, 1, 2, 3, 4. If we go over to the single bond, triple bond, we see those valence electrons don't change because it's the same atoms, but that first oxygen has 7 electrons assigned to that atom. So in other words, we have 6 free non-bonding electrons, lone pairs electrons. Then we have 1 shared electron for a total of 7. Carbon's 4 again, because all those electrons are bonding electrons. And then the last oxygen, the triple bonded oxygen, we have 3 shared electrons and then 2 lone pair electrons, so a total of 5. So if we go ahead and then do the math to calculate that formal charge, which remember we said was valence electrons minus 1/2 time the bonding electrons minus the non-bonding electrons. So that's what we're doing here. And then we see our formal charge. We see the one on the left is 0, 0, 0. One on the right is -1, 0, and +1. The favored Lewis structure is the one in which the atoms have formal charges closest to 0. Well, and it puts a negative form. If there is a charge, then the negative formal charge is on the most electronegative element. So in this case, we can draw this one with the 2 double bonds, and we have formal charge of 0 across the board. So that's what we're looking for. So that would tell us that the C with the 2 double bonded oxygens is the favored structure, because we're looking for the one that have formal charges closest to 0. In that case, they were all 0, so that's great. Another example of this is NCS. So let's take a look at that for a second. If we go through that exercise like we did before and calculate it out our formal charges, and we look at these 3 structures and assign it, we see that the first one, we have -2 on the nitrogen, 0 on the carbon, +1 on the sulfur. The second option, -1 on nitrogen, 0 on carbon, 0 on sulfur. The third one, 0 on nitrogen, 0 on carbon, and -1 on sulfur. So right off the bat, we'll eliminate that first one because we have a -2 and a +1. And we said we like the Lewis structure in which the atoms have formal charges closest to 0. And there we've got a -2, we've got a +1, whereas the other 2, we have 2 zeros and then a -1. So we rule out the first structure. So now that leaves us up to looking at the second and third structure. And both of those, in terms of that first requirement of formal charges closest to 0, are essentially the same. That puts us to our next point, the negative formal charge on the most electronegative atom. Going back to that periodic table, which highlighted electronegativity, we remember that nitrogen was one of those elements that was in red for being more electronegative than other things. So if we have a configuration that has this formal charge more negative on the nitrogen, that's favored because that negative formal charge now is on the most electronegative atom of our choices here. So we've satisfied the smallest atom formal charge, so in other words, closest to 0, and now we've satisfied the second thing we look for is having that formal charge residing on the most electronegative atom. So in this example, the one in the middle, the C double bonded to nitrogen and C double bonded to sulfur, that would be the one that would be most favored based on our Lewis structures and based on the formal charge calculations that we could do. So just to remind you, we calculate that formal charge by looking at the number of valence electrons. We get that number of valence electrons by looking at what column it's in. So is it group 3A, 4A, 5A, 6A, on down the line? That tells us the number of valence electrons. We look at our Lewis structure. The electrons that are involved in a bond, we take half that value. And then for the other electrons, the non-bonding, the free dots, so to speak, we use those. We subtract that half the bonding and half the non-bonding electrons from the valence electrons, and that gives us the formal charge. we'd use that formal charge information here. And then we would go and say, okay, for the different arrangements, what's that formal charge? Which one has the values closest to 0? If we still can't figure it out after that, then we go and say which configuration puts a negative formal charge on the most electronegative atom. And that helps us understand which structure is the correct one. Any questions on any of that stuff? Okay. So once again, this is just a little bit more about Best-Lewis structure. And one thing that you see though, and this was one of the things that we had in lab when we had the benzene molecule, is that sometimes the Lewis structure really doesn't depict things accuracy. And that leads to something called resonance. And so if you recall on benzene, there was a question about the bonds in that, and it didn't really equate to a single bond or a double bond, even though we drew it with an alternating double and single bond. And that's where this concept of resonance comes into play. And when we talk about resonance structures, what we're talking about is that one Lewis structure really doesn't accurately portray what the molecule is doing. So in other words, we're trying to draw these Lewis structures to show how the electrons are shared in a molecule. That's the purpose of the structure. And sometimes it doesn't fit as nicely as we would like. So it's not clearly a single bond or a double bond or a triple bond. And that's where these resonance structures show that there are different ways it can be drawn. And that is an attempt to show what the reality is. And so here for CO2, we have an example of this. So you have this resonance structure where is the double bond, or rather O3, excuse me, ozone, O3 is the double bond to one side or the other. Well, if you really look at the molecule, you see that it's distributed equally. And so it really isn't a double bond on one side and a single bond on the other. What it is kind of a sharing across those three oxygens. But we don't really have a good way to draw that. And so that becomes this concept of resonance structures. Here's the benzene that we talked about in lab. So benzene has two resonance structures. And you see here where you see the double bonds drawn. And then if you shift them all one over to where now the single bonds are double bonds, that's really kind of what's going on. And so it's not one or the other, it's a combination. And that's why a lot of times benzene rings are drawn as this one over on the right with the ring and then the circle inside. And the circle is meant to signify something called delocalized electrons. So delocalized just means that the electrons are spread out and shared over a greater number of atoms. When you talk about localized electrons, which is how we're usually describing them, it's on one atom or shared between two atoms. You know where the electrons are, basically. The delocalized is they're not that constrained. They're more of a shared over a broader area. And that broader area for the benzene ring means we may draw it with alternating double bonds, but really what we're saying is the electrons are kind of smeared all the way around inside that ring. And it's not favored by any one carbon or any two carbons or anything like that. So as you can imagine, there's exceptions to the octet rule. And there's three types of ions or molecules that don't follow the octet rule. So ions are molecules with an odd number of electrons. Ions are molecules with less than an octet, and ions are molecules with more than 8 valence electrons. That's called an expanded octet. And so we'll take a look at some of that here. So the odd number of electrons, to be honest, I wouldn't worry about that. Those are not very common. And the molecules that do have that usually don't stick around long. They're usually unstable or they react pretty quickly in that. So here's a couple examples. You can certainly look at it if you like, but we're not going to worry about that too much because those are not very common. Fewer than 8 electrons, though, that does happen. Boron and beryllium in particular, they can form stable compounds with fewer than 8 electrons. So let's look at BF3. BF3 is actually a pretty common reagent in reactions. And so this is one that you may see quite a bit if you go on to reaction chemistry. So if you have boron, if you fill the octet, what you wind up with is a negative charge on the boron and a positive charge on the fluorine. So down here below in this, you see 4 different Lewis structures for BF3. You have the one on the left, which does not satisfy the octet rule, and then the 3 on the right, which do. So your first thought might be, oh, those ones on the right are correct. But because if you go and calculate that effective charge, or rather that polarity, you'll see that you wind up with positive charge on fluorine, negative on boron. We know from our electronegativity table that fluorine likes to be negative. And so anything that we do that suggests that fluorine is going to have any type of positive charge, whether it's a formal charge or something else, that should make us a little suspicious because fluorine really likes to pick up electrons. It's very electronegative. So that's very unlikely. So even though BF3 is not following the octet rule, some of these other considerations help us understand why that's the appropriate one. So in this case, we're only going to have 6 electrons around the boron and then the regular octet around the fluorine. So once again, if filling that octet on the central atom results in a negative formal charge on the central atom and a positive charge on the more electronegative outer atom, don't fill the octet. And like I said, BF3 is a real good example because the fluorine we know is very electronegative. So if we calculate out that formal charge, so if we go through our process and then calculate out the formal charge on this, and we start seeing something that our formal charge calculations have us with boron as a negative and fluorine as a positive, then that should get us suspicious that maybe this isn't a good configuration. There's also examples of having more than 8 electrons. So when we look at periods 3 through 6, we can use d orbitals. And when we have d orbitals, then we can have something called hypervalent. And hypervalent just means more than 4. So in this case, for PF5, we have 5 fluorines that attach to the phosphorus. So there are some homework problems associated with this. Let's go ahead and take a look at a couple of those, and then you can work on the rest. So let's look at 8.33. So in 8.33, we're going to do Lewis structures for SiCO4 from the silicon and chlorine atoms. So silicon by itself, that atom, we know that's a 4A element, so we would have 4 dots around it. Chlorine is a 7A element, so we would draw 7 dots around it. And then when we go and make that SiCl4 molecule, we can do it one of 2 ways. One is we can use dots all around, or we can do the line to signify a bond and then use dots for the free electrons. And let's do it that way, especially with silicon, because silicon gets a little confusing because the I, the small I with the dot on top, almost looks like 2 more electrons. At least to me it does. And you can see here, I actually in this one on the right forgot to put the I in the air, so it looks like sulfur. So if we have silicon in the middle, 1 electron all around, we take those 7 electrons around chlorine, we have a shared pair between them all, and we wind up with silicon with 4 chlorines around it. When you draw these out, you do need to put in those free electrons around the chlorine. That needs to be drawn in. So the question is, how many valence electrons surround each? We have 8 around each of those. And then we look at how many bonding pairs are in SiCl4. And in terms of bonding pairs, we have 4 pairs of bonding electrons. So each of those lines corresponds to 1 pair of bonding electrons. Okay, 8.41, it asks which of these are polar, and then which is more electronegative. So if we look at all of these, this is where we'd go back to that table that has the polarity, relative polarity values. And we see that for BF, we know that fluorine is the most polar, most electronegative. So we would draw that with the plus arrow, the plus sign on the B, and then the arrow going over towards the fluorine. Remember, when we use this way of drawing it, then the more electronegative atom has the arrow going towards it, and the least electronegative atom has the plus on it. Chlorine, chlorine, whenever you have 2 atoms that are the same thing like that, that's always nonpolar, okay? So the fact that we have 2 chlorines, it's the same atom, the polarities are exactly the same, electronegativities are exactly the same, so it's a nonpolar. SeO and HI, once again, we would use that table, that electronegativity table, to pick out which one has the higher electronegativity value, and that's the one the arrow will point to, and then the one with the lesser electronegativity value will have the plus. Okay, let's take a look at 8.47. In 8.47, we want to draw the Lewis structures for these. So once again, the way you start is you have your central atom. In this case, it's silicon. And now we're going to attach the hydrogens to it. We would look up to see how many valence electrons that central atom has. And silicon is in that 4A group, that 4A column. And so we know it has 4. We know hydrogen has 1. And so then simply we can match up the dots on the silicon and the hydrogen, and then wind up with this silicon atom with 4 hydrogens bonded to it. The next one, we have carbon and oxygen. We know how many valence electrons carbon has, that's 4. And oxygen, because it's in the 4A group, and oxygen has 6 because it's in 6A. So we'd start out by putting those around it. So what we would quickly see, hopefully, is that we're going to have some multiple bonds here in order to satisfy the octet rule. And in this case, you wind up with a triple bond between the carbon and the oxygen. And just to make sure that that's correct, what we can do is we can add up, and we have 6 pairs of electrons that we're sharing. So that's 6 electrons there. We have 2 electrons that are free. So lone pair electrons on each of the atoms, the carbon and the oxygen both. And so by having that triple bond there, we satisfy the octet rule for both carbon and oxygen. If we didn't do the triple bond, we wouldn't have a way to satisfy that octet rule. So SF4, so we have sulfur. Once again, look at our periodic table and see sulfur. We have 6 electrons. And then fluorine has 7. And so actually that is, I think I did the wrong one. I think it's supposed to be SF2. Sorry about that. So SF2, we have 4 electrons on the sulfur. I'll have to work this one out here. We'd have 4 electrons for the sulfur. Actually, 6 electrons for sulfur. So we'd have 6 electrons for the sulfur. Then we would have 2 fluorines attaching and sharing an electron. And then that would leave us with 2 lone pairs around the sulfur. So it should have been SF2, so it should be 2 fluorines attached to the sulfur, and then 2 lone pairs that are free. So we'd have 4 free electrons and 2 bonding pairs with the 2 fluorine atoms. Sorry about that. H2SO4, in this case, it told us that the hydrogen is bonded to the oxygen. So in other words, we have OH groups there. If you go and look at this, we have sulfur, again, with 6 electrons. And then we can pair OH, 1 on each of those. And then we have single bonds to the 2 free oxygens. So 2 of our oxygens are by themselves, and then 2 of the oxygens are really part of OH groups. ClO2. ClO2 is a little bit different because in addition to the valence electrons that we have to work with, we also have, since it's a -1 charge molecule, we have 1 additional electron that we have to account for because of the fact that it's an anion. And so we have chlorine, 6 valence electrons, or rather 7 valence electrons, and oxygen with 6 valence electrons. We can fit those around, and now we have the extra electron from the negative charge to balance things out. And we see that we have a single bond from the chlorine to each of the oxygens, 6 free electrons around each of those oxygens, 4 free electrons around the chlorine, and then it's important when you draw these types of structures, you put the parentheses and then put the minus around it. NH2OH, once again, that one of the hydrogens is attached to an oxygen, so it's an OH group, a hydroxyl group. So nitrogen, 5 valence electrons that we would use. We go ahead, use 3 of those 5 valence electrons in bonding situations, 2 with the hydrogens and 1 with the OH group. And then that leaves us with 1 lone pair of electrons on the nitrogen. Okay, so other than me confusing you on SF2, hopefully that is helpful. I think with drawing these structures, the only way to really do it is to practice and just get a feel for balancing the things out. If we look at OCS to try and figure out what this would be, this is an example of using the formal charge. And so if we take a look at this potential structure, first thing we would do is we would look at the individual atoms that we're working with. So we have oxygen, carbon, and sulfur. And what we would want to do is we would look and see that oxygen and sulfur are both in that 6A group. So they have 6 valence electrons. Carbon's in the 4A, so it has 4 valence electrons. We'd add that up for 16 total electrons. If we draw it out with 2 double bonds, then that tells us we have 8 electron pairs there. Okay, so we have, so let's go ahead and calculate our formal charge. So we have 1/2 times 4, so that's accounting for the bonding electrons for the oxygen, minus 4. So we started with 6, right? We said oxygen has 6. We have 1/2 times the 4, minus 4 for the non-bonding. For carbon, we have 4 valence electrons. There we have 8 electrons involved from the 2 double bonds. And so those are all bonding electrons, so we take half of that. We don't have any lone pairs. And then for sulfur, we have 4 bonding electrons, so it's 1/2 times 4, plus we also have 4 free electrons, so non-bonding electrons. So in each case, what we find is our formal charge is 0 for this configuration. So that's good. The other thing we can do is we can calculate our oxidation numbers. And we did that previously, if you recall that. So oxidation numbers, we know that is based on, once again, where it is in the periodic table. So oxygen is typically -2. Once again, because that's in that 6A, so it likes to pick up 2 electrons to get to the noble metal or the noble gas configuration. Sulfur is the same way, likes to be at -2. Carbon is a +4 because it likes to lose 4 electrons in order to get to that noble metal, so that 4A group. So we have the oxidation numbers there. Okay. Let's talk bond enthalpies for a few moments. So bond enthalpies are positive. So remember, enthalpy is our old friend delta H. So bond enthalpies are positive because bond breaking requires energy. So it's endothermic. So in other words, to break a bond, you got to put energy in. If you're putting energy in, it's endothermic. So the higher the number, the stronger the bond. So this just gives you a feel for some relative bond energies is all we're trying to communicate here. Once again, more bond energies there. So the thing we want to get to, though, is multiple bonds are stronger than single bonds. And so we can measure the bond length. And this is one of the things you did in the lab. You saw that bond length was related to whether it was a single bond or double bond or triple bond. And so as the number of bonds between 2 atoms increases, the bonds become shorter and stronger. And I think everyone probably remembers that from the lab. So that's the key takeaway here. As the number of bonds increase, the bonds become shorter and stronger. So there's a couple of homework problems associated with this. Please take a look at those. We're kind of running out of time, so I'll just quickly kind of talk about this a little bit, is that you have those bond energies that you can use. You look up in the table, and then it's a matter of looking and seeing how many of those bonds are present. So in this case, you have 4 carbon hydrogen. If we just kind of go through the molecules as they're drawn out, in the first one, we have 4 carbon hydrogen bonds. We have 1 carbon-carbon double bond. In the next molecule, we have 2 OH bonds, and we have 1 OO bond. And then in the those are the reactants. And then in the product, we have 2 OH bonds, we have 2 OC bonds, we have 4 CH bonds, and 1 CC bond. So then the numbers that are associated with that are just the bond energies for the different bonds. So in this case, remember, it's a positive number if you're putting energy in. So in other words, to break the bonds, and then to form, it's a negative number. That's why the second part has the summation has the negative in front of it. So what I wanted to communicate here is just that what you're trying to do is you're looking at the bonds, you're counting up the different types of bonds and accounting for them, and then looking up in these tables the bond energies. You're adding up the ones in the reactants and subtracting the ones from the product to get the overall value for the reaction. All right, so that I think we'll wrap up there for today. Just a reminder again that next Monday, the 23rd, we'll have an exam on chapters 7 and 8. On Wednesday of this week, we'll start on chapter 9. So Wednesday, we're starting chapter 9. And then finally, quiz 5 will be a take-home quiz on chapter 9, which I'll probably give out sometime next week. All right, that's it for today. Thank you.